So this week we talked about a few different consequences of chain rule. Last week we discussed chain rule, and we had a homework largely covering chain rule. This week we're going to see ways we can use the chain rule to find more derivatives. So the first problem covers two of those methods. The first question says find dy dx for three functions, well, three relations between x and y, which don't necessarily define functions here. But here, for part A, we have a bunch of x's and a bunch of y's. And what we can do is differentiate everything with respect to x. And when we do that, every time we differentiate something with y with respect to x, the derivative y with respect to x is going to show up. So let's see what that looks like here. So with this, well, the first thing right away, we have something with x's and y's. So how can we differentiate something which has x's and y's? So if there was a noise, that's because my window is slightly opened. It's pretty windy out. So that was coming in. Where were we? So we have this first thing, x over y. Well, you could treat it as a quotient rule. With a quotient rule, the simplification would get a little inconvenient because our goal is going to be to find dy dx. What we can do instead is treat it as a product of x and 1 over y, and then apply the product rule. Applying the product rule here will not introduce any additional fractions we have to necessarily worry about, whereas if we did quotient rule, some extra fractions would show up and we'd have extra simplification. So how would we take the derivative of this? Well, it's a product, so we need the product rule. Derivative of x is 1. Leave the second alone. Plus the first. I'm not going to write a plus yet. Plus the first times derivative of 1 over y. Well, how would we do the derivative of 1 over y? Well, you could write it as y to the negative 1, and you get negative y to the negative 2. You could do that. I'm going to start jumping straight from 1 over y to negative 1 over y squared. It was a derivative observation I made in week 5, I believe it was. And in this week, next week, and maybe the 2 weeks following that, jumping straight from something like y to the negative 1 to negative 1 over y squared will frequently be convenient. So here we have derivative of the first is 1 times the second plus the first times derivative of the second. But remember, we're differentiating with respect to x. We differentiate y with respect to x. We have to apply the chain rule and multiply by the derivative of y with respect to x, which is dy dx, or y prime if you prefer. Any questions about this first piece? So all we did so far, differentiate x over y. And we have a product rule and a chain rule differentiating y with respect to x. Any questions about that? Okay. So next we have e to the 3y. Well, we can differentiate that. So with a more simple way of seeing how this shows up, you can think of it as every time you differentiate a y, a dy dx shows up. But do know that the reason in the background that it shows up is the chain rule. So here we will differentiate e to the 3y. We get e to the 3y times 3. But then we also need a dy dx because we have y as our variable. So technically with chain rule, we get a 3 and a dy dx for e to the 3y. And then we do the same thing on the other side, and I should have been better with the space organization. So I'll just do that now. So first one, we have product rule, x times 1 over y minus x over y squared, dy dx, plus 3 e to the 3y dy dx equals derivative of 4 with respect to x is 0. Derivative of x squared with respect to x is still 2x. Then we have a negative cosecant. Derivative of cosecant is negative cosecant cotangent. The negatives cancel. Our variable is y, so we'll apply the chain rule, multiply by dy dx. So any questions about this first line? Okay, so now we need to solve for dy dx. So I always like to, mark off which things have a dy dx, mark off which things don't have a dy dx, and we can put them all together. Put each thing with a dy dx together, put each thing without a dy dx together, factor and solve. So what I'm going to do is, I guess I'll move dy dx's to that side, move non-dy dx's to this side. So 1 over y is still here. We'll bring 2x over here. So we have a negative 2x. And on the other side, everything's going to have a dy dx. So I'm going to factor that out now. What do we have? We have a cosecant y cotangent y. We also have this negative x over y squared, but on the other side makes a positive x over y squared. And we have a 3y on the other side. It becomes a negative 3 e to the 3y. Factor out dy dx. We have this. And now, I see this last line as essentially the same as solving this equation for x. There are a lot more letters and numbers all over the place, but the math behind solving this equation and solving this equation is the same. Where is was used in that sentence because the subject was singular. So what we have to do, divide by the coefficient. So you get 1 over y, negative 2x, all over this coefficient. Cosecant y, cotangent y, x over y squared, negative 3 e to the 3y. And don't bother simplifying. Any questions about this one? So every time we differentiated a y, we threw a dy dx on. In this first one, there's no dy dx, even though there's a y, because we differentiated to get this only x in applying the product rule up there. So any questions about this one? Okay, what do we have next? X squared plus 3x to the x squared. So here we have y equals something with x's in the base and something with x's in the exponent. How can we take this derivative? Well, we discussed the derivative of x to the x. Here, we can't do a u substitution because notice we have different things here. So we would get different base and exponents, and because of that, the chain rule would not apply. If you had the same thing, you might be able to make an argument that it could, but we don't have the same thing. But what we can do here is take the derivative by turning this thing with x's in the base and the exponent into a product. And we can do that by throwing a logarithm everywhere. So logarithm on the left, we use a natural logarithm, so there are fewer constants to worry about. Logarithm on the left is log y. Logarithm on the right is what? Logarithm of x squared and 3x, all of the x squared. But remember, the exponent using a logarithm property comes out front. and turns it into that product. And now we can differentiate implicitly as in 1. That'll cause dy dx's to show up, well, it'll cause a dy dx to show up. But the derivative we'd have to deal with on the right is just going to be a product rule. And we can do a product rule derivative. So any questions about what we're doing, why we're throwing a logarithm on it? Okay, differentiate with respect to x on the left side. Derivative of log of something is...
Use a logarithm is because there's an exponent on it that you can't use the chain rule for?
Yes, it's because we have x's in the base and the exponent, and they're different. So here, we can't do a chain rule directly because, you could try, letting u be the base, but then you get u to the x squared. You can try letting u be the exponent. You wouldn't be able to get rid of all of the x's with a u substitution. So we throw a logarithm on it, and then we can take the derivative because it's just a product.
Okay, thank you.
So we'll differentiate implicitly. Derivative of a logarithm, natural logarithm, is 1 over the inside. Apply chain rule times the derivative of y, which is dy dx. On the right side, derivative over there, well, we just have a product rule. Derivative of x squared, we have that thing and that thing. Derivative of x squared is 2x. Derivative of logarithm of something. Well, how do you do derivative of logarithm of something? Well, derivative is 1 over that thing times, by chain rule, derivative of that thing, which you can write as 1 fraction if you want, and I will for this problem. Derivative of that thing over that thing. So derivative of logarithm of something, 1 over the inside times derivative. And with a u substitution, u equals the inside, du, or dy du is that, du dx is that. But with logarithms, it is very convenient, especially in a problem like this where we eventually do have to do work with it. It is convenient to just jump straight to derivative of the inside over the inside. And how would that look here? Well, we have a product rule. Derivative of x squared is 2x times the second plus the first times derivative of the second. Derivative of x squared plus 3x is 2x plus 3 over the inside, x squared plus 3x. Any questions about how we got to that line? So this does simplify a little, and I will simplify it that little bit in the next line because, you can cancel out an x. But our goal here is to solve for dy dx. Well, we have a dy dx here. We just have this 1 over y in the way. So we can get rid of this 1 over y by multiplying everything by y. So dy dx equals y. I'm going to leave a gap times all of this because I'm going to erase y and okay, that didn't knock the camera over. I'm going to replace y with what it is in terms of x in a moment. But y times the left, dy dx, y times the right is y times the right. And just writing this as, 1 fraction, which you can do if you want. So an x would cancel here. What would you get? You get 2x squared plus 3x over x plus 3. So, an x cancels here, making that x plus 3. You're left with an x up here. Distribute that x through, you get x times 2x, x times 3. And then, so in part 1a, we couldn't get rid of y in our final answer because we couldn't solve for y explicitly. But here, y is written in terms of x. We can get rid of it, so we should. X squared plus 3x, all the x squared. And don't have to simplify this. Many better things to do with your time than simplify beyond a fraction reduction.
Wait, where did
any-
the sorry, I have a question again.
Okay.
Where
I
did
was just gonna ask it.
that first parentheses come from that you just added in?
Yeah, so here, what was there before was a y, because solving this equation for dy dx, we had to multiply both sides by y. Multiply the left side by y, and the y times 1 over y cancels. Multiply the right by y, we have y times all of this, but y just equals this quantity on top. So, we can get rid of y from our final answer by replacing it with the original function, or the original equation. X squared plus 3x to the x squared. Any other questions about this one? Okay, part C, y equals tangent x to the pi. Well, what do we have here? We have a function with x's in the base and a number in the exponent. We know how to take that derivative using power rule. Pi is a constant. So derivative is pi times the inside, pi minus 1, but then you apply chain rule, multiplied by the derivative of the inside. So with these, with part B, before even doing anything, the key observation for part B was we have x's in the base and x's in the exponent. For part C, before doing anything, the key observation is we have x's in the base, but a number in the exponent. When you have x's in the base and a number in the exponent, you can just reduce it to the power rule. You don't have to throw a logarithm on it if you don't want to. You could have thrown a logarithm on it, and then you'd get a 0 because log of pi, or because the derivative of pi is 0. But here we have x's to numbers, a number. And you can reduce that to a power rule with this substitution, u equals tangent x, then du dx is secant squared of x. Well, if u equals tangent x, y is just u to the pi, dy du, pi u to the pi minus 1 with product rule, and then the derivative is the product of these two. So pi u to the pi minus 1, right here, times du dx. Any questions about this one? May be considered a slight curveball. So any questions about number 1? Okay, what do we have? Number 2, find equations for all horizontal lines tangent to this curve. Well, if you want, you could solve this for y. You'd have to break it into 2 cases, do derivatives for each case, and then go from there. Or we can treat this as an implicit relation between x and y and apply implicit differentiation as we did in part 1A, or number 1A. So we have x squared over 49, y squared over 25 equals 1. Well, we need horizontal lines tangent. And we need to find dy dx and set it equal to 0. To find where they occur, and then we need the actual equations for the line. So let's find a dy dx. Well, we have x squared over 49. In calculus, it's very convenient to rewrite things in ways that make the constant seem more insignificant. Meaning, and you just look at x squared over 49, you may see a quotient. Quotient rule is very complicated, especially when you have a number and you have a derivative of 0 to think about. Less complicated is if we pull that constant out and just treat the x's separately. And similarly for the next thing. I'm hearing a voice. Is that someone asking me a question, or is that someone outside my office? I'm guessing it was not someone asking me a question. Or maybe I'm just hearing voices, you never know. So here, differentiate with respect to x. What do we get there? Well, we get a 2x with that constant. So again, I'm just going to pull the constant right out front. Differentiate with respect to x, we have a 2y. And the constant. But then remember, we're differentiating with respect to x. You differentiate a y with respect to x, a dy dx will show up by chain rule. And then on the other side, constants don't change. As x changes, derivative is 0. Any questions about getting to this line? Okay, so now we just have to solve for dy dx. What do we get? 2/25 y dy dx equals negative 2/49 x. So just subtract the thing without dy dx to the other side. And now what? Well, divide by y. And again, I like organizing constants so that they're all together and non-constants so that they're not. Divide by y, you get x over y. But then you also have to get rid of the 25 halves, or 25 halves, 2/25. So you multiply. You could do it with division. I like to see it with multiply the entire equation by 2/25 by 25 halves, not 2/25. And then this will cancel on the right, on the left. Now, I really don't know right from left off the top of my head. I'd probably make that mistake without even realizing it. So maybe I'll just start this over. We have here dy dx with something in front of it. Get rid of the y, divide by y, and I'll put the y under the x. So that gets rid of y. To get rid of 2/25, multiply everything by 25 halves. On the left side, that cancels to 1. On the right side, well, look, the 2's cancel, except for the negative. And the 25 and the 49 just stay there. So the 2's cancel, except for the negative, the 25 49ths stay there. And now we have a formula for dy dx. Any questions about finding this? So now, what do we need to do? Well, we need horizontal tangent lines. So we need points and slopes, but first we need some points. And how can we find those points? Well, we can find them by setting this equal to 0. How would you solve this? Well, divide by the constant, or just multiply by the reciprocal, or just get rid of the constant. 0 times 49/25 is 0. Solve this for, well, solve this. How could you solve this equation? Well, you can multiply both sides by y, and you get x equals 0. So here we have that the points at which our horizontal tangent will occur must satisfy x equals 0. Well, how can we find the y values? Well, to find the y values, we can go back to our original equation, substitute x equals 0. That should be a 1, not a 0. Sorry. That should be a 1. How do we solve this? Well, just get rid of the 0. Y squared over 25 equals 1 occurs when y squared is 25. So y equals plus or minus 5. Well, now, I guess I probably shouldn't have erased that. Well, actually, I could have, since we said horizontal. So now we can find our tangent lines. The point where one point is 0, 5, with slope 0, which we know by how it's set up, since we're looking for horizontal tangent lines. The other point, 0, negative 5, slope 0, and then we need the equation. So with this one, you get y minus 5 equals 0, which is also known as y equals 5, which you don't have to simplify. I will for one like this. Here, y plus 5 equals 0, also known as y equals negative 5. These seem like relatively simple lines. More on that in a moment, but before I say what I was about to say, any questions on finding these lines? So the in the lecture, the problem which paralleled this used a circle, and I believe I said when x equals negative 3, and on the circle at negative 3, you had a tangent line like that, and you had a tangent line like that. Here, well, we don't have a circle. Something like a circle. So with some algebra, you could have arrived at this answer without doing any calculus. How? Well, x squared plus y squared equals 1, remember, is the circle of radius 1. Why is it the circle of radius 1? Well, distance formula, that the distance formula that you learn is a way of making the Pythagorean theorem look a lot more complicated than Pythagorean theorem. But you can use that to find an equation for a circle, because a circle is the set of points a given distance from something. But why does this give us this circle? Well, when x equals 0, you get y equals 1 or negative 1. When y equals 0, you get x equals 1 or negative 1. What does that have to do with this? Well, it has a lot to do with this, but we're playing around with larger numbers than 1. So what do we have here when x equals 0? When x equals 0, well, that term goes to 0. You need to solve that equation. When x equals 0, how do you solve that? Well, y would equal 5 or negative 5. So what did I say? X equals 0. So y is 5 or negative 5. How about when y equals 0? Well, when y equals 0, that goes away. You need to solve that equation. You get x squared equals 49, which occurs at 7 or negative 7. And right here, we round everything off. Make it look a little more symmetric. That looks a little more symmetric. And right here, we have an equation for this curve, an ellipse with, what are the words they use? Major and minor axis. Major axis is the large one, minor is the small one, whatever that means. The way I like to see it is just by finding these points directly. But with horizontal lines, or horizontal tangent lines, well, you have one right on top, you have one right on the bottom, y equals 5, y equals negative 5. Just like here, horizontal tangent line would be y equal 1, y equal negative 1. But here we're stretching out the circle in the horizontal and vertical directions. In this case, we're stretching more in the x direction. So you could have arrived at 2 using a graph, or you could use calculus. So any questions about number 2? Now, when you, well, I guess I'm talking to a computer, so you don't necessarily have to answer this, but when you discussed ellipses in high school, was it discussed to you in a way that made it clear that an ellipse is just a stretched out circle? I would imagine it may have been, but was not really stressed. Number 3, so that the derivative of inverse tangent 1 over 1 plus x squared. Well, here we're going to use our formula for the derivative of an inverse function. And what is that formula? Well, you may not know it off the top of your head. The only reason I know it off the top of my head is because I've taught it 11 times. But the way we would arrive at a formula for the inverse is by taking the relation, a relation which defines an inverse function. F and F inverse through composition cancel out. Differentiate both sides with respect to x, you get 1. Differentiate the other side, you have a composition, you can find the derivative using chain rule. Chain rule says, take this derivative, take the derivative of the outside, take the derivative of the inside and multiply them. And with our notation, there's derivative of the outside, f prime, leave the inside alone, times the derivative of the inside. A lot of parentheses here. But without having all the restrictions of lined paper, you can size your parentheses in a way that makes it clear which parts are more important than the others. Like, this x is just getting away. But here, applying the chain rule, derivative of the outside times derivative of the inside, allows us to find a formula for the derivative of the inverse.
Dr. Cameron,
Yes.
can you explain the difference between the notation on the left, like the f prime is on the outside versus what's on the right? Because they kind of look like the same thing to me.
Yeah, they do look the same. I agree. They all have, like exponents and things all over the place. The way I like to see the difference between them is by really ignoring what's in here. Now, what do I even mean by that one? I'm not sure. Well, so right here to get this, we're taking the derivative of the first part of the composition, and we're leaving the inside alone. And the derivative of f, which is what we're getting here, derivative of f is just f prime of the inverse. So here we have the derivative evaluated at the inverse. The overall function here is f, derivative of f evaluated at the inverse. So here, the first thing that happens in this piece is f prime. So we have the derivative of something, and this is what we're evaluating that derivative at. So here we have the derivative of f evaluated somewhere. It happens to be an inverse. Over here, well, we use parentheses to sometimes make it clear what's happening first. So here, before we can even talk about this prime, we need to know what the prime applies to. And in this case, this prime applies to all of f inverse. So here, the prime applies to just f. So the derivative in question over here is f, derivative of f prime. Here, the derivative is the derivative of all of this, the derivative of f inverse. So, to see the difference between these two, I think starts at seeing exactly what the prime is attached to. The prime is attached to f over here. The prime is attached to f inverse here. So in this piece, the derivative of f inverse does show up. And here, we're just evaluating it at x. Here, this entire function is evaluated at f inverse of x. Did that make it more clear? Or less
Yes, I
clear?
think that helps. Thank you.
Yeah, so when you look at this, I think the most important thing in dissecting this right side is focusing on where the prime is attached to, on what it's attached to. But in doing this, the derivative of the inverse does show up. And we can solve for that. How can we solve for that? Well, we can solve for that the same way we solved for x in this case. Get rid of the thing attached to x. Get rid of the thing attached to derivative of f inverse. Well, so this is, well, it's the same as the proof we went over in the lecture, but I think a formula like this is kind of hard to memorize with all these primes and exponents all over the place, and the exponents aren't even exponents. They're inverse notation. So if you want to derive that formula, you can. If you want to memorize it, you can. But either way, to find what we want here, we want the derivative of the inverse tangent. Well, if we let f of x be tangent of x, then we put it down here. We put it down here. We get a formula for the derivative of inverse tangent. Well, we have some simplifying to do. First, we need f prime. Derivative of tangent, secant squared. So f inverse prime is 1 over f prime of f inverse. So we're evaluating f prime at f inverse. F prime is secant squared of something. F inverse It's F inverse, which is the inverse tangent in this case. And now we're going to have to figure out why this thing equals this thing. Any questions about how we got to here? Now, there's a good bit of notation to keep organized. In the lecture, we went over this example for sine. With one like this, even another exponent shows up because the derivative of secant squared. In many ways, sine and cosine are the nicest ones for something like this. But how can we simplify this? Well, trig functions define relations between sides of right triangles. Inverse trig functions can be interpreted as angles in a right triangle. And what we're going to do here is make the inverse tangent be one of these angles. So our goal, we want in this triangle setup, we want theta to equal the inverse tangent of x, because this will allow it to simplify nicely. Well, how can we do that? Well, written another way, we want tangent of theta to equal x. Well, tangent of theta, remember, not that. Opposite over adjacent. We want in this triangle opposite over adjacent to equal x. Well, x is also written as x over 1. So with forcing that angle to be our inverse trig function in question, we get those two sides of that right triangle. Any questions about setting up that triangle? I'm actually going to break this into two pieces.
How do we know that that side is 1?
We know it's 1. Well, we're actually forcing it to be 1 because we want tangent of theta to be x. Tangent of theta, opposite over adjacent. We want opposite over adjacent to simplify to x. So one way we can make it simplify to x is by making it really x over 1. You can make the opposite side x, the adjacent side 1, so that right now tangent of theta is forced to be x. And we want to do that because now with that triangle, the inverse tangent is just theta. And now we need secant squared of theta. Well, how do we find secant? Cosine is adjacent over hypotenuse. Sorry, I hear another noise. It sounds like something seeping out, like a water leak or something. Strange things going on in this building today, I guess. Cosine is adjacent over hypotenuse. Secant is that flipped around. Secant, hypotenuse over adjacent. So secant of theta is hypotenuse over adjacent. Well, what's this hypotenuse? Well, Pythagorean theorem makes it the square root of x squared plus 1. So secant of theta, square root of x squared plus 1. So secant squared is that squared. So we get what we want. Any questions about this one? I feel like this could be organized a little better. Right here, all side work in simplifying that denominator. So any questions about this one? Secant is this, so square both sides, and then just rewrite that up there. And you could x squared plus 1 equals 1 plus x squared. So any questions about this one? Number 4. I'm going to do number 5 and then number 6 and then number 4. I have about 25 minutes. I may not be able to finish all of number 4. And it wouldn't be the end of the world if we didn't finish 4B this week, because next week's worksheet is actually a little less work than this week's worksheet. So I may push 4B off until next week. I may not. We'll see how long it takes to do 5 and 6 and 4A. Next week's lectures are, I didn't make them yet, but they are more, so this week, each lecture had a good bit of detail, like working out detail. Next week, one of the lectures is more setting up a large result. So consequently, next week's worksheet will have fewer problems. So I may push 4B off till next week. But let's talk about 5. The height of a cylinder is increasing at a rate of 3 feet per second. So numbers 4 and 5 discuss related rates, where we're interpreting our derivative as a rate of change. But in particular, we have situations which are changing as time is changing. So here, what do we have? The height of a cylinder is increasing at a rate of 3. The radius is decreasing at a rate of 2. How fast is the volume changing when the height is 5 and the radius is 4? So we have a cylinder. Its volume, or its dimensions are changing as time is changing. And this question is asking about an instantaneous rate of change. And we can use our related rates arguments to figure out an instantaneous rate of change. And we'll see that rates show up because of chain rule. But this question is asking about the volume of a cylinder. And in this document called cylinder, we have a discussion about the volume of a cylinder. Let's put some paper behind this so you don't see through it. There. So here we have a box, an XYZ box. The volume of a box, let's see, there is the one side, which is area XY, extended into the third dimension. So the volume would be this two-dimensional area times the extension, XYZ. The same thing applies to a cylinder. A cylinder, a circular cylinder, is a circle extended into the third dimension. With our units, we have, let's see, radius R. So the volume, or sorry, the area of this circular slice is pi r squared. Extend that h units. Gives us a volume of pi r squared times that extension h. On the second page of this is a discussion of surface area of a cylinder. Next week, there will be a question using surface area, so that'll show it. But here, we need the volume of a cylinder, which is pi r squared h. Well, r and h now are functions of time, and v. So volume, radius, and height are all changing as time is changing. So we can retranslate this question in terms of those rates. The question says, how fast is the volume changing? How fast is the volume changing? The volume is changing by that derivative, the volume with respect to time, dv dt. How fast is the volume changing when the height is 5? The height is 5. When the radius is 4. The radius is 4. But we also have other information. We have information about how the height and radius are changing. Sentence 1 tells us that the height is increasing at 3 feet per second. That was 3, right? Yes, 3. So dh dt is 3 feet per second. And it's also telling us that the radius is decreasing at a rate of 2 feet per second. And the radius is getting smaller as time is changing. And with derivatives, we can interpret that as a negative rate of change. So dr dt, negative 2 feet per second. Any questions about about translating that question into a calculus question? Okay, so now R, V, and H are all functions of time. So if we differentiate with respect to time, all of these rates are going to show up. So differentiate with respect to time. And differentiating with respect to just means in our, let's say, a couple of different ways you could see it. In our page or our document with 22 derivative rules from weeks 5 and 6, we were always differentiating with respect to x. It was our variable that we were controlling in a sense when taking a derivative. You could also see that as, with the slope of the tangent line, slope of the secant line argument, differentiate with respect to time means that that's what we're pushing to 0. Either way, that will, for those of you who take a Calc 3 or beyond math course, that will show up. It'll be much more important to clarify the details. For our class, we'll pretty much always be differentiating with respect to x or time, t. But here, functions of time, derivative on the left side, well, derivative of v is just 1, but then we're differentiating with respect to time, so we get 1 times dv dt. What do we get on the right side? Well, pi is a constant. That's just going to get in the way. So I'm just going to pull it out front to begin with. We have here 2 functions of time. R squared and h are both functions of time. Take the derivative, we're going to need a product rule. They're both functions of time. So in differentiating each one, rates are going to show up. Derivative of r is 2. Derivative of r squared is 2r times dr dt by chain rule. So first, product rule. This first piece gives us 2r dr dt. Leave the second alone, so leave h alone. Plus, leave the first alone, we get r squared. Derivative of h. Can you hear that car alarm that's going off? Okay, it just stopped going on. Okay, it just started again. Where was I? So we have a product. Derivative of the first is 2r to the first times dr dt. Leave the second alone. Plus the first times derivative of the second. Derivative of h is 1. But then with chain rule, you get 1 times dh dt. And pulling pi out right at the beginning, I think, makes this much, much easier to organize. Any questions about getting to this line? So the reason this was number 5 rather than number 4 is because this derivative is much more complicated to come up with than, for example, the 4a derivative, because we had to interpret it as a product, and because in doing that, a rate will show up with each piece. But once we get here, we just need to substitute all these numbers. It's already solved for dv dt. So what do we get? We get 5, 2rh, 2 times 20 is 40, times another negative 2 gives us negative 80, plus r squared, 16 times dh dt, 16 times 3 is 48. Wow. Where did I get 5 from? I'm not sure why I even thought of 5 at that instant. Pi, maybe because pi and 5 sound somewhere. Those make a -32. So we get -32 pi, and what are our units? Volume, so feet cubed per time. Any questions about this one? Okay. Number 6, and we'll probably have time for 4A. We may have time to set up for, oh, we'll see. What's in 6? Okay. Yeah, we'll definitely have time for 4A. 6, find each limit using L'Hopital's rule. Now, L'Hopital's rule allows us to compute some limits provided they take a certain form, an infinity over infinity or a 0 over 0. And we can find these limits using derivatives. So part A, limit x to 4 that function. Now the directions here say find each limit using L'Hopital's rule. On a test, odds are it won't say definitely using L'Hopital's rule. So it'll say find limit, you may use it if you want or something like that. But here we definitely do have to use it because it tells us to. Well, why does it apply here? Well, you try a substitution of x equals 4, what do you get? You get 16 minus 24 plus 8. Well, that's 0. Over 16 minus 28 plus 12. That's also 0. The L'Hopital's rule does apply when we get a 0 over 0. On a test, it will say something like justify each application of L'Hopital's rule. And it would a sufficient justification would be like just making a note up there that you do get one of the forms on which L'Hopital's rule applies. Next week, we will cover some more L'Hopital's rule questions. And we will see that figuring out when it applies will take some work. But what does it say? It says that if you get a 0 over 0 or an infinity over infinity, you can compute the limit by computing a different limit. The different limit is given by the derivative of the top divided by the derivative of the bottom. Derivative of the top, 2x minus 6. Derivative of the bottom, 2x minus 7. And here, if we can substitute, we're done. If not, well, we have more work to do. But here, we can substitute. And what does it give us? It gives us 8 minus 6 on top. It gives us 8 minus 7 on the bottom. So that's 2 over 1, which is 2. So on a test, if you have this problem, it wouldn't say you have to use L'Hopital's rule. Those do factor. So if you would have preferred to factor, you could have done that on a test. Any questions about part A? B, limit x to infinity, x squared negative 5x positive 1 over x cubed 3x squared negative 1. So with this limit, you could, divide everything by x cubed, and go from there. You could, unless you're told not to, make the coefficient observation and realize degree on top is less than degree on bottom, so limit is 0 as x goes to infinity. Or you could use L'Hopital's rule, which we have to do here. Now, why does it apply here? Well, a polynomial as x gets large is dominated by its largest term, meaning as x gets large, the only part of the top that matters is the x squared portion. The only part of the bottom that matters is the x cubed portion. Because for large x values, cubes get larger much faster than squares, and so on. But why does that matter? Well, it means that as x goes to infinity, the top goes to infinity because it's dominated by x squared. The bottom also goes to infinity because we have a positive number and we're cubing it and it's getting large. That'll keep getting larger. Infinity over infinity, L'Hopital's rule applies. That limit equals this new limit. Same limit as x goes to, same variable, and, well, infinity is not a number. Same limit, but different function. Derivative of the top, 2x minus 5. Derivative of the bottom, 3x squared plus 6x. Well, how can we take this limit? Well, again, you let x go to infinity, this top goes to infinity because of the x term. The bottom also goes to infinity because of the x squared term. Meaning we can apply L'Hopital's rule a second time. As x goes to infinity, top and bottom could both go to infinity. Derivative of the top is 2. Derivative of the bottom is 6x plus 6. And as x goes to infinity, top remains 2. Bottom goes off to infinity. So keep dividing 2 by larger and larger numbers. That will keep getting smaller and approach 0. Any questions about number 6b? So next week we will see some more types of equations that we can apply L'Hopital's rule on. For example, we haven't taken any limits of functions with x in the base and the exponent. Taking derivatives, not limits. That's next week. But for now, let's go to 4a, and we might set up 4b because it does have the same setup. 4a, a rocket is launched vertically. It is tracked by a radar station 3 miles from the launch site. So we have a radar station 3 miles from launch site, and the rocket goes up vertically. If the distance from the rocket to the radar station, so the rocket is being tracked by this line, and the information given is about the distance between the rocket and the radar station. Okay, if that distance is increasing at a rate, what is the vertical velocity when the rocket is 5 miles from the radar station? Well, before interpreting anything besides the picture, we would need to consider our variable quantities. So here, that 3 is always a 3. It's not a variable quantity. What are our variable quantities? Well, the rocket is going up. Where the rocket is changing. So let's call that x. The distance from the rocket to the radar station is also changing as x changes. Let's call that y. And with that, we can translate our question. Well, any questions about getting this picture first? Okay. So what does this question want us to do? If the distance from what is the vertical velocity? Vertical velocity. Well, that's measured by x. Well, the position is measured by x. So the vertical velocity is measured by the derivative of x with respect to time. So we want to find dx dt. When do we want dx dt? Well, let's see. When the rocket is 5 miles from the radar station. When y equals 5. So y in our diagram is measuring the distance between the rocket and the radar station. What else? The distance from the rocket to the radar station is increasing at 500 miles per hour. So the distance from the rocket to the radar station, y, is increasing at 500 miles per hour. So y is changing as time is changing at 500 miles per hour. Any questions about translating that question? So I wrote y equals 1 off of the line because I noticed, did I say y equals 1? I wrote y equals 5 off the line because given a y value, there's also going to be a corresponding x value. So here x would be 4 because it's a what, a 3, 4, 5 triangle. Or you could have done the Pythagorean theorem directly since that's a right triangle. 3, 4, 5 triangles show up a lot. So we don't have an equation yet, but we can find an equation because we have a right triangle. So we get 9 plus x squared equals y squared. X and y change as time is changing, so we can take the derivative with respect to time. Derivative of 9 is 0. 9 doesn't change as time is changing. Derivative of x squared. X and y here are functions of time. Derivative of x squared is 2x. And then chain rule throws out a dx dt. Derivative of y squared is 2y. Y is a function of time as well. So the chain rule throws out a dy dt. It's very important to keep in the back of your mind that x and y are functions of time. So when you differentiate with respect to time, the rates show up by the chain rule. Any questions about that? Because now we just have to, we have 4 unknowns, 3 of them are known. So we can substitute, we need to solve for dx dt. I would continue this under there, but I don't have room, so I'm just going to go over here. So dx dt equals what? Y over x dy dt. So divide by 2x, the 2's cancel, you get y over x times dy dt. Y is 5, x is 4, dy dt is 500, and 5/4 of 500 is 625, because 1/4 of 500 is 125. Any questions about this one?
I was just wondering why, when it's like the derivatives, like the hypotenuse or whatever, the rate of change of the like hypotenuse doesn't have to be faster than the rate of change of x.
Are you comparing this 500 to this 625? Is that?
Yeah.
So why is that? Okay, I never thought of that. Let's see, why would that be? Well, right here, this rocket is going up. So this rocket is going up, it's measuring its change from this unit. It's looking at that line. So this is going up, this is getting away from this point at a certain rate. But if you move this point over and you look at how this is going up, well, it's going up away from this point at a certain rate. But if we take this point and move it all the way over there, maybe if we exaggerate it, throw it like 100 miles in that distance, it's still getting away from this point at that same rate. But how is it getting away from this other point? Well, this is what? It's closer to this point because it's a vertical line than it is to this point. So how far it's getting away from this point is traveling on the vertical line, which is a shorter line than traveling on the diagonal line. So it's getting farther away. It's going away from this point faster because it has less distance to travel to get to that line. That made a lot more sense in my head than it did when I turned it into words. But these are all rates of change, and we're looking at how the distance from this point is changing and the distance from this point, how that's changing. So this has less distance to travel when you're to consider when you're taking its rate of change. And this has more to consider when you take its rate of change. And because of that, it's going to get away from this farther or faster than it gets away from that.
Okay.
I'll try to think of another way of explaining that because it was clear in my head, but turning it into words didn't feel as clear as it could have been. Any other questions about this one? Okay, well, we won't do part B. Your equation is going to relate that angle theta with a trig function. But we will do part B next week. Next week's worksheet will have fewer questions. But there's no homework this weekend, so it would be a good weekend to catch up on our worksheet information. Or you can go outside and enjoy your weekend. It is an Easter weekend, so I hope you're able to enjoy that. If not, enjoy your April Fool's Day, and I'll see you next week.